Hello everyone, welcome to my talk. This work focuses on the safety of reinforcement learning and especially the robustness to adversarial attack. I'm Zikang Xiong, and this is a joint work with Joe Eappen, He Zhu, and Suresh Jagannathan. Let me introduce the motivation of our work. First, the neural network is not robust to adversarial attack. Small perturbation may cause a system crash. For example, the left end is controlled by a deployed neural network policy. If there is no perturbation, it can work normally. However, when we apply small perturbation to the initial state of the end robot, it flips after several steps. The perturbation is very small and usually is not noticeable. Thus, applying adversary perturbation can cause great threats to the neural network controlled system. Second, adversary training is widely used as a defense technique, but it cannot support the post-deployment setting, which means the deployed policy are not allowed to change. This is realistic because it might be infeasible to stop running service. Also, the deployed policy may have some designed properties, and they may not exist after retraining the policies. To address the above concerns, we proposed and evaluated a post-deployed defense approach. The reinforcement learning system is a closed-loop system like the left figure. The agent takes action to the environment, and the environment gives feedback to the agent. Based on the feedback, the agent takes another action to the environment. The feedback to the agent includes the state ST and the reward RT. The goal of this attack is to find a small perturbation to a state ST, and this small perturbation is expected to cause unsafe behavior in the future. More specifically, let's look at the example on the right, a trajectory starting from state ST. In the future, it will visit state ST plus 1, ST plus 2, etc. ST plus 1 has the closest Euclidean distance to the unsafe region. We mark this distance as FST. Then we apply Bayesian optimization to minimize the FST and find an adversary state S prime T. We bounded the distance between S prime T and ST in a reasonable small distance. For a successful adversary attack, the trajectory started from S prime T is expected to intersect with the unsafe region. We use a shield mechanism to defend against the adversary attack. By adding a shield in the closed-loop system, we can enhance the robustness of this system without touching the pre-trained neural network agent. The shield takes the action AT and the state ST as input. If it finds the ST is potentially unsafe, which means there will be an intersection with the unsafe region in the future, it will use a safe action to replace the AT. Otherwise, the shield will output AT. Thus, we expect the shield can always output safe actions. For example, when the shield finds the S prime T is a potential unsafe state, it will output a safe action, and this safe action will change the next state to a safe state. Now, let's take a close look at how the shield works. To mark a state is unsafe or safe, we need to train a classifier. We call it detector. The detector is trained with the data collected on the attack phase. After getting the detector, giving a state ST, we can decide this state is safe or not. If this state is safe, we will use the original policy of the agent to output action AT. Otherwise, we use the auxiliary policy to output an action as replacement. These two policies are trained with different objectives. The original pre-trained policy is trained with a performance objective. For example, the robot should run fast with less electricity cost. The auxiliary policy is trained with the safety objective, which is to maximize the closest Euclidean distance between the trajectory and unsafe region. Thus, the shield can combine the safety provided by the auxiliary policy and the performance provided by the original policy. Because we train the auxiliary policy with safety objective, it's not necessary to have good performance. For example, when we start the anti-robot from an adversary state, although the robot does not flip, it also does not move and thus has low performance. However, if we combine the performance of the original policy and the safety of auxiliary policy, because the auxiliary policy only intervenes when necessary, the shielded policy is safe and performant. We compared the performance of the original policy and the shielded policy over 20 benchmarks, and the experiments show that the shielded policy have very close performance with the original policy. Because we introduced a new safety reward here, one natural thought is that we can use the safety reward to shape the training reward. However, here is a fundamental issue for reward shaping. Suppose the safety reward is the blue curve in the figure. The performance reward is the yellow curve. If the shifted reward is the sum of the performance reward and the safety reward, we will get the green curve. Notice that the maximum of the training reward is not necessary to be the maximum of the safety reward and the performance reward, because now the reinforcement learning algorithm will optimize on the shifted reward. We may not get the best safety and performance. On the contrary, because the shield only intervenes the original policy when necessary, it will not face this issue. In this table, we summarized our experiment result of the attack and defense. The first column is the benchmark name. The robot name is before the dash, and the reinforcement learning algorithm is behind the dash. The second and third columns are the dimension and the trajectory simulation lengths of those benchmarks. The fourth column is the L1 norm used to bound the attack. The fifth and sixth columns are the attack successful rate of random attack and Bayesian optimization-based attack. The seventh column is the percentage of adversary states we removed with shield, and the last column is the percentage of adversary states reduced when we attack again on the shielded policy. The experiment results show that the shielded-based defense can significantly enhance the robustness without touching the original policy. Because we introduced a neural network detector, it can also be the attack target. Thus, we provide the experiment to demonstrate the robustness of shield mechanisms when the detector is under attack. We attacked the detector with FGSM. The attack will try to make the detector always mark the state as safe. The attack norm we used here is as same as the one we used to attack the original policy. The experiments show that unless the FGSM attack successful rate and the attack frequency are as high as 80%, the shield-based defense will not fail. This is because even if we fail to detect the potentially unsafe state once, the detector still has opportunities to detect the potential unsafe state in the future, as long as current state has not hit the unsafe region. Thus, even when the detector is under attack, the shield-based defense still can provide good defense results on those benchmarks. In summary, we generate a shield for deployed policy to adapt to adversary attack. There are 3 steps to generate a shield. First, collect the safe and unsafe trajectories when attacking the original policy. Second, train the detector with the collected data. Third, train the safety auxiliary policy with safety objectives. Finally, we can assemble all those components for a shield. Our experiment results show that the shield defense can effectively enhance the robustness of a deployed policy. The shield mechanism itself is also robust to adversary attack on detector. We packed all of our experiments in a Docker image and is available online. The link is given below. That's all for my talk. Thank you.